This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question BC2, namely areas in polar coordinates. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by developing the formula for the area of a region bounded by the graph of a polar equation. Then I'll illustrate this formula with an example, solved both analytically and using technology. Next, I'll consider the area of a region bounded by two polar curves, and I'll illustrate this concept with an example also. My first objective is to develop or derive a formula for the area of a region bounded by the graph of a polar equation. To do this, first recall the area of a sector of a circle. Suppose r is the radius of the circle and theta is the radian measure of the central angle. Then the area of the sector of the circle is 1/2 r squared theta. This seems like a very reasonable formula. The area of a sector is proportional to its central angle. Pi r squared is the total area of the circle, and theta divided by 2 pi is the proportion of 1 revolution. Let R be the region bounded by the graph of the polar equation r equal f of theta, and the rays theta equal a and theta equal b. And we'll assume that f is a positive continuous function, and that 0 is less than b minus a is less than or equal to 2 pi. So R is the shaded region in this figure. To approximate the area of the region R, first divide the interval a to b into n equal subintervals of width delta theta, and label the endpoints of these subintervals as theta sub 0, theta sub 1, theta sub 2, all the way down the line to theta sub n. The rays theta equal theta sub I divide the region R into n smaller subregions with central angle delta theta equal to theta sub I minus theta sub I minus 1. Next, choose an arbitrary value theta sub I star in the ith subinterval. The area of the ith subregion, denoted delta A sub I, can be approximated by using the area of a sector formula by considering a circle of radius f of theta sub I star. The central angle is delta theta, and again the radius of the circle is f of theta sub I star. This approximate area of this sector is illustrated by the shaded region in this figure. Using the formula for the area of a sector of a circle, the area of the ith subregion, delta A sub I, is approximately 1/2 f of theta sub I star squared times delta theta. An approximation for the total area A of the region R is obtained by adding the area approximations for the subregions. Now, it seems reasonable that as n increases, this approximation for the total area A of the region R improves, and this approximation is a Riemann sum. Therefore, the limit as n goes to infinity of this sum is, by definition, this definite integral. And finally, the area A of the polar region R is given by this definite integral. Here's an example to illustrate this area formula. Let's see if we can find the area enclosed by one loop of the polar curve described by r equals 4 cosine of 3 theta. Well, here's a graph of this polar equation, and I'll consider the loop in the first and fourth quadrant. The top half of this loop is traced out for theta between 0 and pi over 6. So I'll find the area of the top half of that loop and double the answer to find the total area of one loop. In the first step, I used the formula for area, the expression for r, and symmetry. I multiplied by 2 to find the total area of the loop. Next, I squared the expression for r and used a half-angle formula. I found the antiderivatives term by term, and evaluated, and simplified. The total area of one loop is 4 pi over 3. And here's a technology solution to this example. I used the TI-Nspire to find the exact symbolic answer. Suppose we want to find the area of a region bounded by two polar curves. Let's let R be a region bounded by the graphs of the polar equations r equal f of theta, r equal g of theta, theta equal a, and theta equal b, such that f of theta is greater than or equal to g of theta is greater than or equal to 0, and b minus a is between 0 and 2 pi. The region R is shown in this figure. Well, we can find the area of the region R by simply subtracting the area inside R equal g of theta from the area inside R equal f of theta. So the area of the region R is given by this definite integral. Now, one note here. Remember that a single point has many representations in polar coordinates. So we need to be careful in finding the points of intersection of two polar curves. In this example, let's consider the polar curves described by r equals sine of 2 theta and r equals cosine of 2 theta. First, let's find the area of the region that lies inside both curves. And then let's find the area of the region that lies outside the graph of r equal f of theta and inside the graph of r equal g of theta. Well, here's a graph of both polar curves. The letter A here, or the region little a, represents one of the 8 subregions that lie inside both curves. And B, or the region B, represents one of the 4 subregions outside the graph of F and inside the graph of G. I'll leave it to you to check that these graphs intersect in the first quadrant when theta is equal to pi over 8. To solve the first part of this example, I found the area of half the region A, doubled it to find the area of region A, and then multiplied by 8 to find the total area inside both curves. To solve the second part of this example, I found the area of half the region B, doubled it to find the area of the region B, and then multiplied by 4 to find the total area needed. It's amazing that this answer is exactly 1. And here's the technology solution. I hope this video provides some insight into finding areas in polar coordinates, a few AP Calculus type problems, and the use of technology to solve these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.